got the whole thing.
This is for
You have to.
well, yeah, but we don't want the water back and like recycling the water.
Outside?
You're right, but
Yeah,
happen to be down there.
it just how expensive. Yeah. And for the actual
I don't think the reactor is.
I don't know where it is.
I just want to make sure that that is clear. I stopped that.
Yeah, it is bad.
I could have said, oh,
Breathing, yeah, and then this stuff also, a lot of people, it is more used method way. I used to no, what I mean is they use the like it's over a bottle.
Yeah, that's what it's gonna happen.
I just
it'll last until your next bucket.
That would be
General Sullivan. I was calling all.
yeah, but isn't that what we need? That's in 2 weeks. But for the point, yeah, it's not that slow. Yeah, it got me now. Last time I always had no, actually, so what is it? More standardized. Once, yeah, and then once they my point there being that
Whoa.
Oh, I thought you were saying.
So that's the thing
All right. Chapter 4, page 20. I will give 2 more examples today. On Wednesday, we'll cover reactive distillation. We'll show you how Eastman Chemical intensified the 9-column process into a single column. That's the real process intensification. On Friday, no class. Finish your proposal. All right, are you ready? Chapter 4, page 20. Phenol. water, butanol. This is the old Hershey data book, but now you can get all the pure component boiling point, azeotrope from Aspen. Let's start from page 21. In this example, this is the low scoring binary azeotrope. (99.5) intermediate boring. So this is a distillation boundary dB LB to IB or IB to HB. In this region, those boiling, ice boiling, HB1. In this region, 93, 118, 182, HB2. Now, given feed is right here, you want to get both components, phenol. How do you separate them? Let me enlarge this. Come down a little bit more. All right. This is a two-phase region. Azeotrope. This is organic layer. So if you get a column like that, so I put down a column column 1, D1, B1, no, yeah, this, wait a minute, column 1, D1, F. F, in this region, minimal boiling, B1, right? What do you do with D1 and B1? Whenever you see an azeotrope, there is a distillation boundary here, you can use a decanter D1W, D1O, D1W, D1O. Aqueous layer, organic layer, two-phase region. Vapor, liquid. Vapor, organic layer, Now, you got D1W, D1O. D1W, D1O, okay? D1W here, for this column, you can get water product, okay? So you can go to a column, C2, overhead 93, bottom 100. This is also B2. Angel, B2, water, right? So, by using this decanter, you get water. Now, this D2, obviously, at this point, on the plot, is actually a recycle, right? Fit the decanter. Okay? Now, column 2, B1, there's no azeotrope, so this column, this is phenol. Normal butanol. So C3, overhead, lower temperature, bottom, D3, normal butanol, bottom, phenol. So we got all three products. Even though phi is here, originally, without crossing the distillation boundary, you cannot get water, right? Is this easy? Make good use of decanter. Now, let me see. I want you to do something. $4.28. Uh-oh. F is here. Can you two work together? You sit together. You can come up with a solution. Let you work on that a little bit before expanding. Phi is here. So LB, IB, HB2, HB1. No. In this region, this is IB. Okay, in this region, HB1, 93, 100, 95, all right? And IB, HP, that is a dB. Can you try it? Get all three products. I put a decanter here. D10, D1W, D1. There it is. Can you finish? Need two more columns. One on this side, one on this side. So, if I send this back, F1. D10. F1. Need two more columns to get phenol, to get water. Any idea? Now, you see this F1? This field. How do I produce D1? In your column, in this region, whatever column you have, overhead is the lowest volume agental, right? In this region. So, D1. D1, there's no agent, so this line is phenol. This line is normal butanol.
Can you put the paper down a little? Just hold it down a little. Or zoom out. Thank you.
Smaller. That's good. So, F1, C1, D1, D1. B1, C2, high boiling, low boiling. Now I'm missing water. Which stream I have to use? This. This is a column by itself. this length is water. That length is axial. So, another column. Over here, D1. You can call that B1, D2, B2. And this over here, axial. Bottom, water. What do you do by axial? Send it back. Send it back. Why is a simple message? Whenever you have two-phase region, make good use of this tie line. You get all three products: water, ethanol, phenol. Okay? Aha! The next one is challenging. Famous. Acetic acid water separation. The problem is not with azeotrope. Does not form an azeotrope. The problem is the following. Look at page 77. Okay, I can see it. Let's look at here, acetic acid, water, adding a salt. You can pick several different types of solvent. In fact, later on you'll find out four solvent on page 95. But now, let's look at here. Phe is here. Acetic acid, you cannot get pure water because of tangent pinch. So you draw a y-axis diagram. Up to here, this region, y-axis curve almost become tangent. tangent pitch. That's the trouble. So, the person who did this project, Jeff Sirola, design team head Eastman. Design expert knows how to think. He was very skillful. Even became president of the institute. So now, you find a solvent, creating an azeotrope with water. Not only that, that's a two-phase region. You say, why are you doing like this? Crazy. Now, this low boiling solvent, you'll find what it is in a minute. In District 9, that dot to here, to the end, about 90% pure low boiling solvent. This tiny portion, 10% water, and there is a two-phase region. So, feed adding a solvent. Instead of using distillation, you use liquid-liquid attraction, feed solvent, feed solvent. And then you have extra product, raffinate product, extra. This is liquid attraction. There is a trick. Look at step 1, step 2. You draw a straight line. That means feed solvent in this length is feed. That is solvent. Jeff Sirola is smart. He said, make sure solvent to feed, flow rate ratio will give you number 3. That is the line between extract and raffinate. What is location of point 3? Right here, this determines. You look at here, 3 such that 4 and 5 will intersect with two-phase envelope at this point. So this extra point is fixed by connecting 4 and 5. With that, this is your attractor line. Key to creative solution is this point. This point connect 4 and 5, intersect with attract. From here, you connect resonate the 3. So now, extract is right here, right? So, you make this a column. Right here, low volume, acetic acid, minimum volume. So, there is distillate, this is bottom. Column 1. Now, when there's azeotrope, what do you do? Here's a column. Column 2. Column 2, this line is raffinate. This line is solvent. Raffinate solvent. Right? Column 1, you get solvent, raffinate. Once you get this raffinate, you can still separate. You look at here, raffinate. Can you see it? You can see it. Azeo, water. This is column 2. Okay. Column 3. This gives you azeo overhead, water bottom. Combination of liquid-liquid attraction plus distillation plus two-phase tie line decanted. To overcome the tangent pinch. Otherwise, conventional acetic acid water distillation column. People who do not understand this principle get over 100 trays, very tall column. Any question? Let's try another solvent. Okay. Now, here's another solvent. Low boiling solvent, 34.6. Added ether. No significant azeotrope. This is tangent pitch. So, Phi solvent. Solvent. Here, mixing point. For extract raffinate. This point, you look at here, 1, 2, 3. Feet, attractor, look at this point, and acetic acid plus, let me see, Phi plus solvent. This point is fixed. How, if you draw this column, that will intersect at this point, okay? So, this is on one straight line, this on another straight line. So, this key to solution, location of this point, such that that intersection point is on this straight line. With this, here's one column, Phi acetic acid. Solvent, okay? Now, solvent, raffinate water. Solvent, raffinate water. This raffinate solvent, E, give me solvent. This point has acetic acid water, that's right, okay. You look at this point on this line, there's no azeotrope. This whole thing here, this length is solid. This length is water. That is a column. Anyway, you get a solution on page 82. There are solutions of different solvent, but go to page 95. Let me minimize it. This says solvent 1, 2, 3, 4. In actual industrial practice, how does Eastman do it? Come up with a preliminary flow sheet and do your Aspen simulation of all of them. Pick the best one. This page appears in the Foundation of Computer-Aided Process Design Conference. Okay? That's where I got this information. They keep all the solvent name confidential. Some of them can't figure it out. The key, you notice, attractor. What normally would not think about using liquid-liquid attraction combined with distillation in complex flow sheet. Okay, on Wednesday, I will teach you principle of drawing RCM for reactive distillation. And we want to invent ethyl acetate Eastman chemical process on RCM. Okay, that's it. The form doesn't work. This is the new form, they send it to you.